right. Hi, everyone, and welcome to Zymposium. We're going to be taking a break from our AI adventures, so I'm sure we'll be coming back to them soon and look at a more ZIO-specific topic of FiberRefs. And we've done, I think, at least one session on FiberRefs before, so we're going to do a little bit of a review just so we're all on the same page of what are they, and particularly when might we want to use them. And then we're going to go in particular into a feature in ZIO 2 where FiberRefs actually use this thing called patch theory. So we're going to talk about what that is and why we needed to bring that in and how that helps us when we're writing our programs and when we're using ZIO. So hopefully we will have some fun here. All right, let me share my screen and we'll get started. All right, so let me make this a little bit bigger for folks. So we've just got our, one more side. There we go. Now we're nice and huge. All right, and make this a little bit smaller. All right, so we've got our basic hello world application, so we can make sure that things actually want to compile, which is great. And so let's start with just a little bit of context on first we'll do what is a FiberRef, then like why or when would we use FiberRefs? So what is a FiberRef? Why would we use one? And then we'll get into this discussion of patch theory and how that actually powers some of the FiberRef functionality in ZIO 2. So what is a FiberRef? So a FiberRef we could think of as ZIO's equivalent of a thread local in Java. So just like a thread local has a different copy for every thread, a FiberRef has a different copy for every fiber. So let's see what that looks like for a second. So let's change this, and we'll start with not a FiberRef. So I'm going to make a ref that is 0, and then I'm going to create one fiber that's going to update the value of the ref and get it. And I'm going to debug this, and I'll call this left. And then I'm going to do right. I'm going to debug this. And then I'm just going to join them both to make sure that we're all actually done here. Yield unit here. Just format this for a second. And so my expectation here is that this ref is something that is shared between these different fibers. So when one of the fibers is updating it, they're changing the value that's going to be visible to the other fibers, which is what makes a ref useful. A ref is a way to communicate between fibers. So we might imagine maybe this ref is like how many fibers are done, and each fiber is decrementing it when it's done, and then the last one, when it knows that it's the last one, is going to do some kind of line down. And that only works because the changes made by one fiber are seen by the other fibers when we work with a normal ref. And so our expectation here is that one of these is going to print 1 and one of these is going to print 2. And the order is going to be indeterminate because we're forking both these at the same time. I would guess statistically, since we're doing this one first, we're slightly more likely to get this one printing first. But let's try running this program and let's see what we get. And so, yep, we got exactly that. We got left being 1 and right being 2. And I think probably most of the time we're going to get that just because this is going to run immediately. So let's contrast that with the behavior of a FiberRef. So if I want to make a FiberRef instead of a ref, I just do FiberRef.make. And they support a lot of the same operations. So I think the rest of this code should compile as written. But now let's try running this. And so notice here, now both of them are always going to print 1. And that's because each of them got their own copy of this FiberRef. And when they updated it, they just updated their own copy. So if on the same fiber, we make a further change, so let me say on this left one, say I maybe do this again. So I'll do ref.update and get blank +1. And I'll move this debug into here. And I'll debug again. I'll call this left 1 and left 2. Let's run this. So we'll see that the changes we make, we are actually making changes, and those changes are visible on this fiber, but they're not visible on the other fiber. If I copy this down here, and maybe I'll make these 2, 4, and right 1, right 2. Right left gets 1 and 2, because the second call sees the result of the first call. Right gets 2 and 6, because this saw the result of the first call. So that's the what of a FiberRef. A FiberRef is again, like a thread local in that it's some value that we can update, but when we make those updates, they're only visible on our fiber. They're not visible on any other fibers. So, okay, that's the what of it, but that explanation may not necessarily be the most satisfactory, because I don't know about you, but I actually don't work with thread locals a ton. I think I have a couple times when I've done logging type stuff with like other logging frameworks, and maybe partly that's just because I use ZIO, so then I just use the FiberRef instead of the thread local. But you know, I don't think the thread local is necessarily the most common thing you run into. So I think it's just like a thread local has a little bit of a limitations as an analogy that way. So let's try to get into a little bit more of the why here. So in terms of why we would want to use a FiberRef, the way I like to think about it is use a FiberRef whenever you want context, and we'll define that term, what we mean by context here, that is not reflected in the environment type. And so you say, well, what do we mean by context? And the definition I would give you would be context is all the information our workflow needs to run that isn't reflected in the arguments to the function that creates it. So if I have let's say I have something that's like let's say persist user, right? And maybe this needs a user. And let's not even worry about its type here. Let's just leave this as question mark. And we'll create some just trait user so that this actually compiles. So here this, and we'll assume this is creating some ZIO right now. We'll put any for all these types just because we haven't filled them in yet. So this context is everything that this persist user workflow needs to do what it's doing, other than the arguments that we're providing here. In this case, other than the identity of the user, right? Imagine maybe this is actually like find a case class user, and maybe there's an ID that we would like it to be a UUID, but we'll just make it a log for now. So anything that this workflow needs, other than this, is part of this context that we're talking about. So what might that context be? Well, I mean, it could be a lot of things. It might be, in this case, it definitely needs to be some database interface, right? Because if we're going to persist this, we need to persist it somewhere. And this doesn't say where we're going to persist it right now. It also is maybe some logger that we're going to use. Maybe it's some metrics provider. Maybe it's some additional logging span, or yeah, it could be a maybe it could be some configuration options, like how many times we should retry. This is all stuff that might be needed to actually implement this persist user in a sensible way that's going to do what we want here. And so whenever we have context like this, there are basically two ways that we can represent that context. So two ways to represent context. One of them is the ZIO environment type. So we can imagine here, right? Maybe I think a pretty obvious thing here might be to say, well, this can't be any for the environment type. Maybe this needs to be something like database. And maybe this is actually going to be a trivial function because the database is going to have a lot of the functionality to do this. And hold on one sec, because I see someone raise their hand. So let me see if I can. Participants. Hey, Pavel, did you want to ask a question?
I'm sorry, database is in the return type, and we are talking about the input types. So we cannot talk about database in the return type of ZIO. Right?
We are talking about it in the input type here, because this is the environment type of ZIO. So this is representing the services that this workflow requires to run. So right now we're saying that this workflow
I thought
requires a database to run.
Output object. This is not an input object. This is what the function produces. And in order to work, it needs the input object. Okay.
No,
maybe.
so here this persist user is returning a workflow that is going to require a database to run.
Oh, okay.
So yeah, maybe I'll sketch that a little bit more. But yeah, that's a great question, because yeah, if that's not making sense, then other things are not going to make sense.
Okay, thank you.
Yeah, definitely. Let me just undo this thing. Let's see. Okay. So that's a great clarification, that this function right now is a function that, given a user, is going to produce a new workflow. And just like a reminder of the ZIO type signatures, is when we have a ZIO REA, what that means is that's a workflow that requires services R and can fail with an E or succeed with an A. And I'll just comment this out so I can use the actual ZIO. But so what we're saying right now is that this persist user, I'm going to give it a user, and it's going to give me back some workflow that I can run that's going to do something. And so maybe I'm going to have a database here, and maybe at least a lot of this is going to be pretty simple, because maybe the database itself is going to have a persist user. Maybe it knows about the user, or maybe this just knows about an ID, say. And maybe this doesn't return any value, it just does the persisting. Maybe this will fail with some kind of IO exception, but right now we'll just leave it as nothing. And then we could imagine that at least our simplest implementation of this might be something like ZIO.service with ZIO, and we're just going to call persist user with the user ID. So that's one way we reflect context that we need, right? This persist user workflow needs some context. It isn't just something we're giving as a function argument. So we put it in the environment type. And then later on, when we want to run this, we're going to need to actually provide it with a database. So maybe I'll create a little object database, and I'll do something that maybe I'll call dummy. And this will be a layer that is going to produce, it should not be housed, hasn't learned about ZIO2 yet. But so this could just be zlayer.succeed. So I don't need to really do anything to create this dummy database. And maybe this is just going to have a ZIO.debug statements. Maybe it'll just be ZIO.debug persisting user ID. And so then if I go back to my method here, so now maybe I want to persist user1. I'm going to try to run this, and I'm going to get one of these nice error messages that says, okay, well, this thing needs a database, but you haven't provided the database. So you've got to give me one. And so maybe I'll do provide database.dummy. I think it may just be, okay, I'm just going to do, I need to define these in separate files if I want to use the provide automatic layer construction, but I don't really need that here. I'm just going to use provide layer. And now I can run this program, and it prints the persisting user1 because that's what my dummy implementation does with this. So this is using the environment type to reflect context, and that's, I think, a very classic pattern with ZIO. And so that's always one option we have of how we want to represent this context. There's another option that we have, though, which is using a FiberRef. And in this case, this context is not reflected in our type signature anymore. And so let's explore a little bit of what that looks like. So far we've got this persist user that is just going to just use a database, which is great. But let's say we also want to do some logging around this. So one way I could do that is I could just create a new logging tree. And we're going to just put aside for a sec the fact that logging is integrated into ZIO2, just because this will be a kind of a simple example of like a functionality we could use here, and we'll kind of build off of this. So I could have some logging interface that just lets me log a message. And I could basically do the same thing that I did with database. So instead of this just needing a database, it could need a database and logging. And then maybe I'll do the same thing. I think I'm going to need to give some type annotations here now, because now I just need to know which one it's doing. So this would be database. This would be logging. Let's see. Oh, I'm doing this in the opposite order. Oh, yeah. Obvious little silly thing I'm doing. So this is logging, this is database. And then I'm just going to get the message that I need to actually provide something else here. So let's just do that for a second here. So let's do object logging. And then maybe I'll have a no-op logger, which is just going to not log anything. And so now that I've got that, I'm not going to use the automatic layer construction just because this is the same compilation unit right now. So I'll just use the classic ++ way. And now I can run this. So this works totally fine. And I can clean this up slightly by adding these accessors here. So if I wanted to, I could do def persist user. And usually, yeah, Copilot is quite good at implementing these accessor methods, which is nice. So I'll just do those, which so compiles, and then I can clean this up and I can just make this whole logger.log database.persist user. A logging. And what I think I have extra. And then persist user. User. It's just too big. Oh, this should be. This will take a long. Okay. So I can always use the environment to reflect context, and I could just keep adding things here. So we could go back to like our list here of everything that we might need, and we can just add more and more stuff here, right? So if I also need some configuration here, I could make this and config and metrics, and I could just keep going with that. But at a certain point, that starts to maybe feel a little bit annoying here of we're like cluttering up our method signature with a lot of things that are maybe details that we'd like to be configurable in some way, right? We'd like to be able to provide, to customize how we're gonna log in some way. But in a way, it doesn't seem as critical to this method as the database does. And maybe one clue we could have for that is, it seems like we don't have a database. There's no sensible way that we're going to be able to implement this method to do anything. Like its whole point is to write something to a database. So if we don't have a database, we're kind of SOL here. Versus the logging, it seems like maybe we're going to have some default logger. Maybe that default logger should log the console, or maybe it shouldn't log anything at all. But it doesn't seem like it's as critical in a way to reflect in our type signature. And we can imagine if we just take all these things that are potentially going to be used by this and put in type signature, the type signature is going to get pretty big pretty quickly. And so that's where this FiberRef pattern comes in here. And so let's say that instead of all of this, I said I want to be able to use logging, and I want to be able to customize it, but I don't want it reflected in the type signature. And so what I can do here is, instead of all this, I can move this into a FiberRef. And so let's see what that looks like. So I'm going to comment this line out for a second, and I'm going to get rid of this here, just so this compiles. Then we'll kind of redo this the FiberRef way. And so in this case, I'm not necessarily going to need this here. It's the same way. Maybe bring back some variant of this. I'll keep this logging interface. But then what I'm going to do is I'm going to create a FiberRef. And maybe I'll call this current logger. It's usually a pretty good name for this. Or current XYZ is kind of a good name for the FiberRef for XYZ. And so this is going to be a FiberRef that contains this thing. And oftentimes a good pattern is to create this FiberRef as just its own static singleton value. And so for that, we can use the unsafe interface on this. And we're going to need to do our little unsafe.unsafe. Plus unsafe. Just to say, yes, we know we're doing something that's not just describing something, but is actually doing something. And here we'll have some default implementation that we want to have here. So in this case, or the other thing we can do is we can make this optional. So we could either have like a no-op logger, or we could have an option of a logger. I think here maybe I'll create the no-op one. So we'll kind of recreate that. But now maybe this is just going to be the actual thing instead of a layer. And maybe I'll make this private here because I'm just going to use this internally. And so that's going to be the value of this thing. And so now I can re-implement my log method, but now this is just going to have any instead of the logging and the environment type here. And all it's going to do is it's going to get the current logger from that FiberRef, and then it's going to use it to log a method, or log a message, I should say. And so now I can comment this back in. Okay, format, and hopefully I'll fix the little indentation. Okay, my indentation is good now. I guess that's significant white space, yay. And maybe I'm actually gonna change this to, I'll call this default. And maybe I will actually do something like, just so we can actually verify this is doing something. So now I can run this. And so we see I did log something. And so what I've done here is I've retained that same functionality, right? I'm still able to use logging here, but I've removed it from this method signature here. And I still have all the same ability I had before to customize the logger that I'm using. So let's say I have this, and I'm like, you know what, this is annoying. Like, I don't need to log everything, especially when my database is already doing that internally. So then what we could have is let's create another val silent. So this is going to be another logger that's going to not do anything at all. And so let's say then I want to run this whole thing, but I want to make this logger, I want to make this go away, right? So we don't log this thing. So I could do logging dot current logger, and I could use this locally operator, which is going to take a new value for that FiberRef we have. So in this case, I'm going to want to use silent logging for everything inside this block. And now you see I replaced this logging implementation with a new logging implementation that doesn't log anything. And so I have full ability to customize the logging I'm doing here. I have the same ability that I did when it was in the environment type. I'm just no longer reflecting it in the type signature. So these are two different ways of reflecting context here. And they both have their own advantages and disadvantages. So the environment type is very explicit, right? I look at this and I know there's no way I'm going to run this without providing it with a database. And the compiler is literally going to stop me from running this without providing a database implementation. So I think if we think about kind of benefits of this, this makes the dependency or the requirement for context very clear to the user and what that context looks like. And this, I would say, is particularly good for cases where there isn't a sensible default value, or where the context is, you might say, key to the logic of the workflow, right? So if we go back to our persistence example here, this database seems pretty integral to what we're doing here. I mean, this is like the whole point of calling this function. So I think it makes a lot of sense to reflect this in the environment type of like, hey, you can't persist something unless you have a database, and won't even let you run it without that. And it makes very explicit what the interface of a database that you need to provide if you want to do that. Versus if we think about this logging, it's more, I'll use the word implicit, though I know it's like dangerously overloaded with how many ways implicit is used a different way in Scala. But here, the context requirement is not reflected in the type signature. So advantages of this would be keeps the type signature clean from what you might think of as implementation details that we want to be able to change if needed, but we don't want to put so front and center for our users, right? Where here it seems like, okay, this stuff does some logging. It's great. It's always good to do logging when you actually have issues and you want to figure out what's going on, and you definitely want to be able to customize your logging. But I think we probably say that's not really key to what this method is doing. Maybe it's going to log some stuff. Maybe it's going to report some metrics. We don't need to make that explicit in the same way. And I think maybe we don't want to here. And this really makes a lot of sense. You typically need to have some sensible default value for the context, right? So like for the logger, we said, well, we can have a no-op logger, or maybe it's a console logger. You can debate what the default is, but like that made some sense versus like if you're like, hey, I need a API key for this thing. Well, you know, there's probably not a default API key. So that maybe does need to be in some kind of config that gets reflected in the environment because there's not a default value there. Okay, so that's an overview of when these two options of hopefully like why we would use a FiberRef and some of the advantages and disadvantages of doing so. Let me just check in on the Discord here, and then we'll keep going. All right, it seems like we are either this is all making sense or you're all bored out of your minds, one of the two. So we will proceed here. But definitely feel free to comment in the Discord or raise your hand if you have any questions as we're going along here. So, okay, so this is, so now I think we understand the what of a FiberRef and the why of a FiberRef. So let's now start to think about this and get to why we need this catch theory concept and where that fits in here. And so to motivate that, I think I'm going to create one more of these interfaces. And actually, I'll do it two different ways, maybe. So one way is I'm just going to create a couple different FiberRefs. So I'm going to create one that maybe I'll say retries. And this is going to be, say, a FiberRef of int. We'll implement in a second. And this is going to represent how many times we should retry the database operation if it fails. And then maybe we're going to have another one that we'll call maybe retry interval. And I could use a duration, but right now I'm going to be boring, and I'm going to do, like, let's say this is going to be an int as well. And this is going to be like duration in milliseconds between each retry. And so we could make each of these easily. Let's see. I think I need to give a little bit of int. Okay, so we're going to retry 3 times by default. And we're going to do it at 100 millisecond intervals. Okay, that doesn't seem crazy. And so let me simplify some of this stuff. I'll leave that, but I'm not really even going to worry about that for now because I just want to like focus on these 2 values here. So what happens if we modify both of these? So let's say I have a workflow here where I say I want to do, I want to retry 5 times instead of 3 times. And I want to retry at 200 seconds. And then I'm just going to get each of these. And I'll debug these. Uh-oh. Okay. So let's try running this. And so we saw both of these changes, which makes sense here. We changed one and then we changed the other. These are both 2 separate things. So this works completely fine. And then we get both of them and we see those results. Now, what happens if let's play with a couple of variations of this. So one that I just want us to kind of, should hopefully be obvious, but I just want us to see is, let's say I do retries.set 7 here. So I run this, I'm gonna get 7, right? Because when I do 2 sets, last one wins. That kind of makes sense, right? So that's kind of one observation we can have here is we set the FiberRef to 2 different values. The last one kind of makes sense. And so let's then look at one more variation of that. So let's say that I do 2 updates in parallel. So I do retries.set 5.zipar retries.set 10. So here the result's actually going to be indeterminate. But let me run this and let me go over a couple things for us. So I think most time we are going to get 10 because the last one is going to win, right? That's what we just saw here. And in this case, just the left-hand side, just because it's on the left, is going to get started first. And since they don't take any time, the left-hand side is going to finish first. So fine. So one thing we see here is this idea of the last one winning. But the other thing that's important to see here is that this is illustrating a principle that when we join a fiber, the parent fiber is going to get the FiberRef value of the child it joined. Right? So here, what the ZipPar thing is doing internally is it's forking one fiber that's doing this, and it's forking another fiber that's doing this. And so if we didn't have this idea that when we joined a fiber, the parent gets the value back, then when we did this, and we did these checks, we actually wouldn't see 10 at all. We would just still see the original value of 3. So the fact that we're seeing 10 here, or that we're seeing 5, is showing us that when we fork a fiber and then join it, we see the changes that it made. And that's really important because whenever we're doing program with ZIO, we want to honor this concept of fork join identity. And so another way of saying this is making our program more parallel shouldn't change the meaning of the rest of our program. So think about if I did this. If I did this, this zip is just run this thing and then run this other thing, all right? It's the same as this, or it's the same as if I just did these on separate lines. So if I just do zip here, then on this same fiber, I'm going to set it to 5, then I'm going to set it to 10, and then I'm going to get it. So in this case, I'm clearly always going to get 10. So what this fork join identity principle is saying is just because I make something parallel doesn't mean that its meaning should be different. Does that idea of fork join identity make sense to everyone? Okay, cool. So let's make this a little bit more complicated and kind of get to our real motivating case here. So, okay, right now I'm just playing with this retries, but let's go back to what I was doing originally, where I think I set the retries to 5 and I set the retry interval to 200. And let's run this and let's just see what we got. So we get 5 and we get 200. And that makes sense, right? That's what we expect. This is basically just the same thing as the very first example I showed where we did this. The only thing I've done is I just refactored this to be a zip, which is literally the same operator. So this is just 2 different ways of writing the same thing, but I'm just going to do it to set up my comparison. So here we do this, we get 5 and 200, right? And that makes sense because on this one fiber, we're setting retries to 5, then we're setting retry interval to 100, then we're checking them both. So we're all on the same fiber, we're all going to see this. And so let's do, yeah, so Nabil says after assembling the parts, you get still a car, right? Yeah, that I think is a great way to think about it. And so here, let's do ZipPar, and let's run this. And we see we get the same thing. So far, we're getting the results that we expect, right? Everything is making sense. But now let's go back and let's think about doing this maybe in a little bit of a different way. Because if we scroll up here and we look at these, I think this is a perfectly fine way to do this, right? I mean, if we wanted to do it this way, we definitely could. But we might also say that maybe we don't want to have separate FiberRefs for each of these 2 things, because maybe we feel like these 2 things are pretty related to each other. And in fact, maybe we want to be able to add more things as well, because maybe eventually we're going to want other parameters here. And we want a way to add them without having to so explicitly change our code here. So let's look at an alternative way of encoding this. And I'm going to start with a pretty simple way just to kind of motivate this. And so maybe I'll say we're going to have a retry config. And this is going to be a FiberRef that's maybe a map, or not, sorry, it's not string int because we don't have, but it's going to be a map from string to int. And maybe this is going to have the same default values, right? Now, yes, this is right now a little bit less strongly typed than this one was, but let's just roll with that for now to kind of illustrate what we're doing here. So now I've got this retry config here. And so let me now play with it to use the retry config. And let me maybe make a couple of methods on the retry config. So why don't I make a method called def with retries. And so this is going to take the new retries that we want. And this is basically going to just update the FiberRef with the number of retries we want. And then I'll create another operator, def with retry interval. And this is also going to be responsible for updating this. And so let's go ahead and implement these. So retry, so this retries one, we could, oh, I think maybe I want to give this a different name. Maybe I'll just call this N, just so I don't overload this. So what I could do is I could just say for map in retry config.get, and then I set it to having retries equal to the value that I want. And similarly, I can do the same thing here. And one thing to notice here is I'm using get and set separately. And if I was doing a normal ref, that would not be a good thing to do because I wouldn't have a guarantee that these are being done atomically. But when I'm doing a FiberRef, each fiber is always updating its own copy of the FiberRef. And each fiber is the only one running the fiber, right? The fiber, by definition, is like a thread. It's only being run one thing at a time. And so with a FiberRef, we're free to do as many separate gets and sets as we want. And we know we're the only one modifying our copy of the FiberRef. So it's totally fine for us to do this. So now let's update our example here. And so I'm going to do with retries, and I want to do 5. So I'm going to set retries to 5. And then I'm going to set the retry interval to 200. And then I'm going to change this to be retry config.get. And so let's try running this. And so we see we got exactly what we expected, right? Where we updated the retries to be 5, we updated the retry config to be 200, and we got exactly those out. So that makes a ton of sense. All right, now here's where we're going to get into the problem. So what do people think is going to happen when we change this and we do zip par here? Anyone want to type the answer into the chat? Yeah, so Kenji said that the last one is going to overwrite the first one's result. yeah, so let me try changing this to a zip par. Yeah, look at what we got here. So we did change the retry interval to 200, but we lost somehow our update to the retries here. And again, it's a little bit non-deterministic here based on the order, but just given how short these effects are, it's typically this is going to be first and this is going to be the second one, just because we have to start one before the other. But so why is this happening? Well, based on what we've said before, so imagine we have the parent fiber, and it starts out with this map from 3 to 100. Right? Then we have the child fiber. And when it's done, well, sorry, not child, but let's call this the left fiber. And when this is done, it has, right, it updated the retries to 5. And then we had the right fiber that left the retries alone, but updated the retry interval to 200. So now we're the parent. And so we said, let's say we happen to join the left fiber first, because it's just the one we happen to run first. And so we say, okay, got it. I'm going to take your value and I'm going to make it my value. So the parent fiber joins the left fiber, and its value after that, it takes the left fiber's value. And so it has this. And then the parent fiber joins the right fiber. And it says, okay, I'm sorry, my mouse is all placed there. And so it's going to say, okay, I'm going to take the right fiber's value. And the right fiber's value is this. And that's how we end up with this value here. But we know this is wrong, right? I mean, one, we're missing one piece of information that we intended to update. We clobbered ourselves, you could say. And two, we violated that principle that going between zip and zip par shouldn't affect the meaning of our program. So how do we fix this? It's not completely obvious how we do it here, because I mean, if these are just the values we have, they're the values we have, right? I mean, we had an original value and we have a new value from this one. And if we have just these two arbitrary values, we can use one or we could use the other, right? We could either keep the parent value or we could keep the child value. And if we keep the parent value, then we're clearly going to be wrong, because then we're going to ignore both updates. And if we keep the child value, then, okay, we're going to get one update, but then when we get the other child value, we're going to get the other update, but we're going to clobber the first update. So it seems like we're kind of damned if we do, damned if we don't. And this is where this idea of patch theory comes in. And so one way to think about this is think about how GitHub works, or think about a version control system in general. So one way to, like, I mean, let's just make this like super practical in our lives. Imagine that this is the master branch, right? In ZIO, this is the master branch, and Adam, right, checks that out and he creates his branch, and in it he updates this thing this way. And then Kit comes along, and on his branch he updates things this way. And then Adam merges his PR, and then Kit merges his PR, or the other way around. And what Git is usually smart enough to do, it actually may not do it if it's on the same line, but I think if we imagine that we like split these out on separate lines, is we're going to be able to merge both of those, and we're actually not going to have a merge conflict when we do it. And we could kind of ask basically the same question we had here of like, how does GitHub do that? Because if all GitHub has is like, hey, here's the original blob of code and here's the new blob of code, then it's kind of in the same position that we were at before of you just have these two blobs of code and you either take the old value or you take the new value, and both of those we can prove lead us to incorrect results. And so the way that GitHub deals with it, and the way this patch theory deals with it and we deal with it, is we introduce a new concept of a patch. And let me go to the interface of FiberRef for a second and show you what this looks like. Why did that not go? Oh boy, I'm going to the FiberRef that we made here. Okay, hold on a second. Let me see. Can I actually get to the actual FiberRef file? No, I didn't want URL. Hold on one sec. Let's see. Am I doing something with a content clicker here? Okay, this is very frustrating, and I guess this is another fun VS Code thing here. Let's see. I'm going to try one more, and then otherwise maybe I'll just do a different screen share. Let's see. None of those are the ones that I want. This is not the one I want. Okay, so I'm just going to do a new screen share here. Oh, give me 1 second. Let's see. There we go. I think. There we go. Okay. I've got the FiberRef here. Oops. Okay. So this is looking at the actual code for a FiberRef. So every FiberRef is a FiberRef of some type, right? So this was, in our case, it was that map. And then every FiberRef has a patch type, which describes some patch that knows how to apply one change to this type. And to be well-defined, a patch supports a couple of different methods associated with it. So one is that we have an ability to diff two values and create a patch. So going back to the GitHub analogy, you can imagine, I mean, we can literally do this, right? We have one branch and we have another branch, and we can diff those two to create some type of patch that is going to describe the differences between those two things as some kind of data structure. So maybe in the actual Git case, it's going to have a list of different files and line numbers and what things were. It could be represented a bunch of different ways, but what this says is whatever its representation, we have to be able to create one given any two files or branches or whatever the value is that we're working with. So one thing is we have to be able to diff them. Second thing is we have to be able to combine patches sequentially, which just means do the changes from this patch and then do the changes from this other patch and return some new patch that describes that. So that's basically, in a way, you could think of what happens every time you squash your commits, right? Imagine every commit is a patch, and when you squash them, you now have one commit that describes everything you did in either two commits, or if we can do this with two of them, we can do it with two and then another two, or however many we want. So we can combine however many patches we want. And then the final thing we have to be able to do is we have to be able to apply a patch, right? So if we have some original block of code in GitHub and we have some patch, we have some diff we created, we need to actually be able to apply that to get to a new piece of code that reflects those changes. And those are basically the features that define a patch. And so if we go back to our original example, and we won't do code yet, but let's just kind of think about what this is. As soon as I, one sec, find a code here. So now let's imagine, how do we solve this with patch theory? So let's go back to kind of our examples of what each of the fibers does. So the parent fiber still has this value of retries 3, retry interval 100. So that's fine. But now this left fiber, if we had this world of patches, we could say, right, we haven't at least written this in our own code yet. We could say the left fiber doesn't just return this map with retries 5 and retry interval being 100, but returns a patch that says set retries to 5. And then this right fiber, it doesn't just return a new map, but it returns a patch that says set retry interval to 200. And then when you're the parent fiber and you join the left fiber, well, then you say, okay, I've got a map of this, and I've got a patch that says set retries to 5. So I can apply the patch to the value, right? And I can get this. And then the parent fiber joins the right fiber. It says, okay, well now, this I think is not quite right. My current value is I've got 5 and 100, and I've got a patch that says set the retry interval to 200. And so, okay, well, I'll just set the retry interval to 200. And now I'm going to get the right thing here. And so we can map what we described basically back to those operators we had. So this here, this is the patch operator. And this is another use of the patch operator. And here, for the left fiber to get this patch, it needed the diff operator. Because what this left fiber really did is it said, well, hey, when I started out, this is what I had, right? This is what I had when I originally checked out the branch. And then I did some edits. And by the time I was done, here's what my branch looked like. And so if I diff these two things, I can see the change I made was I set the retries to 5. And the right fiber can do the exact same thing. So if we could use this patch theory, we could solve this problem. Can everyone see how that would work? I'm going to check in on the chat one more time. Okay. You have not responded, but I'm going to take silence as a symbol. Oh, okay. Hold on. We gotta raise hands. So let me get over here. Yes, HKT, higher kinded type.
Hey, what do we do? Maybe I'm jumping ahead, but what do we do when we have conflicts?
Well, so ultimately, hopefully we're going to have something where we don't have conflicts, but if we're literally updating the same thing, so like we're both trying to update the retry interval, at some point someone's going to have to win, and that's going to be the same case as if we did it in sequentially, or if we just had a primitive example, right? If we go back to like our original example of when we just had these as separate FiberRefs that just worked with ints, if we have two people that set retries at different values, one of them is going to win. We're going to have that last wins philosophy. So that's always going to be the case if you get to what you could think of as like atomic elements, right? I mean, go back to even the GitHub analogy of if Kid and I are both like setting the same variable in the same line to two different values, one of them is going to have to win and one of them is going to have to lose. So what we're trying to do here is we're trying to preserve the maximum information possible and avoid clobbering each other when we're modifying different parts of some larger structure. Make sense?
Yeah, thank you.
Okay, definitely. All right, let me, okay. So that's all nice, but we would like to obviously not have to manually implement all this logic for diffing these things and doing this patch theory stuff ourselves. And so that's what ZIO gives us. So let's go back to ZIO for a second and look at this, and then we'll use it here. So far this FiberRef says, hey, I don't care what the patch type is, as long as you can diff things, as long as you combine your patches, as long as you can patch things, then I'm happy. But ZIO also provides some nice tools for us, so we don't have to kind of create these ourselves. And so before, we use this this make operator on a FiberRef, which is kind of the simple constructor, so to speak, and is a good one for where the things that we're putting in the FiberRef are atomic, right? Where they're just like a Boolean or an int, where like some value has to win. But if we have a larger structure, we've got a bunch of variants here, and kind of the most fundamental is this one called make patch. And so this one asks us for an initial value, just like we had before, but it also asks us for this differ thing. And so a differ, we go to this file, basically wraps up all of this patch stuff in one data type. And so a differ is parameterized on two types. It's parameterized on a value type. So that would be like in the GitHub case, it's like a document, or in our case, it's a map, and a patch type. So that might be some kind of representation of a diff or a patch in GitHub, or in our case, we'll see it's this thing called a map patch. And it just has those same operators. So it says, well, if I have a differ knows how to do the combining of patches. A differ knows how to diff two values to produce a patch. A differ also has a concept of an empty patch. So there should always be an identity that like the empty patch is the patch that applies no changes. And then we know how to apply a patch. And then a differ does a couple of other cool things, that it has some operators that let us combine these two different differs. So you can imagine that if we have a way to diff one value and a way to diff another value, we can actually diff a tuple of those values. And similarly, if we have differs for two values, we can diff something that's either one or the other. And so there's a bunch of logic to do that. There's this transform operator that says, hey, if we know how to transform a value to another value and then back, if we can basically say these two values represent the same information, then we can diff the new value, even though maybe we don't have a differ for the original value. And then we also have a bunch of different differs built in for different data types. So like if we have a chunk, we can diff values by applying changes at different indices. If we have a ZIO environment, we can treat that as a map and we can patch values at different keys. We have one for maps, in fact, so which is going to do that logic of patching values at different keys. And so those then get used back in this FiberRef, where we can either use this make patch constructor ourselves, and we can provide whatever differ we want, or for common data types, there are actually already variants that use the right patches. So like this one is going to use the make set operator, which is going to do a make patch with the set differ. Or I think I'm at least hoping to make my life easier. Maybe we don't. Let's see, do we have a make map? Maybe we don't have a make map. Let's make map. We don't have a make map. Okay, well that's fine. I will use the, maybe I should add one, but we'll use the other one. So what our plan then is going to be to do is if we go back to that make patch. So I'm going to be able to make one of these FiberRefs.with patch that knows how to do the patching in a more sophisticated way than just last value wins. And I'm going to do that by providing my starting value, but now also by providing a differ, and I'm going to use the map differ. And yeah, in retrospect, I should make a make map variant to make this easier for myself next time, but that's fine. All right, so let's go back and do that, and then we'll try to kind of conclude here because this ended up being a little bit of a longer session, but that's fine. All right, so I'm going to go back to my Zymposium code and scroll over there. Okay, so what I'm going to want to do then ultimately to fix this after a little diversion into theory is I'm going to want to make this retry config. So instead of make, I'm going to do make patch. And maybe I'll give myself some space here. And I'm going to need to remember the arguments to this thing. I'll make that little compilation go and help me out here. Yep, so I need an initial value. I need a differ. And then I need some for control. Okay. So, and maybe some of these could have default values, but that's fine. I think this is really, I should just add the map method. So let's go back to this. So here I can do differ. I think it's called map differ. Let's see. Oh, I think I'm going to need to specify the type parameters here. And I think these are the type of the keys and the values. So I think this can be a string int. Let's see if I can. String int. I believe this is a map patch. Maybe let me go back. Hold on one second. Just going to check the type signature. Oh, I see. Right. And we find the right. So this expects a function actually that's going to be a way to diff the values to the point earlier about whether we have conflicts on the keys. And since we don't have a more sensible way to resolve conflicts, if two people update the same key, other than last one wins, we're going to use the update differ for that. And then in this low-level version, we also need to provide a fork and join function. I'm just going to double check the signatures of these. Give me a sec. Yep. And I'm not going to want to apply any special changes just when I fork. So God, I believe I can do maybe I'll just extract this out. And now I just need to give it its type parameters, I believe here. Working. Okay, yeah. Okay. Okay. So now I'm telling it how to diff these things. And now if I want to, this actually has additional information that is has the patch. I don't think I need that here. And so now this is, if I've done this right, this should be working. Otherwise I may have to debug this offline, but let's see what we've got going on here. And so look at that. So now we got exactly what we wanted, even though we did this thing in parallel versus sequentially, right? We got this change and we got this change because we used this patch theory and we had these tools internally that helped us do that in a ergonomic way. So like we didn't have to actually implement the diffing or the patching ourselves. That was taken care of for us. And if we wanted to, let me see if I can do this as like a final thing. So we might say, well, this, maybe I'll do this as actually, maybe I won't do this right now. But basically we can use some of those operators on differ, like those ways we can like zip two differs together, and the way we can transform two things into each other to work with even nicer data types like this. So like maybe let me see if I can just do this quickly. So like maybe we'd like to make something that's a little bit nicer. Maybe this should be like a case class that has this inside of it. And then maybe I want to make this a FiberRef of retry config. So I could update this to be 3,100. And now I could do, let's see if I can do, so I can do differ dot update dot, I believe it's called zip. Let me just double check my names here. So I could do differ dot update. I think I may need a type parameter. Let's see if I'm zip differ update int. And then I can take that and I could do transform. I'm not sure if this is quite going to work, but let's see if that's going to work for me. And then I'll come back to this one in a second. And then I'm going to need to update some of my other stuff of, let's see, I'm going to need to update my little with methods. So now this is going to be copy retries equal n. And this isn't even a map. Just call it try config. And then this can be the same thing, except this will be retry interval goes in. And I'm going to see if I can resolve the others here. That one over here. I'll come back to that in a sec. Oh, I should have used this. Okay, now it's this. And this needs to be parentheses. So this is valid syntax. Let's see. And then this is going to need to be a function. So I think this could be retry config to a tuple of retries and retry interval. Let me format this. It's a little more readable. Still not the most readable, but maybe we'll go with that. And then this can just be the empty one here. Yeah, I can probably write this more nicely, but right now I'm just gonna try to just quickly do this. Okay, and now let's see if I can run this program. This would do the right thing. And again, we see I got exactly what I wanted. I got my updates that reflected both of my changes, and now I have a more sophisticated representation of this in this custom data structure. And again, I didn't have to kind of manually do the logic of patching. I just put my, just use those operators on differ. So I think probably in most of your work, you won't, I typically will not need to do this. This is done internally by ZIO for like when you update the ZIO environment. This is how we make sure that different updates to the environment get all applied in the correct way. So I think most of the time, probably this is just going to be taken care of for you by library code that uses this to do the right thing. But I guess if you are ever doing something with a more complex structure in a FiberRef, this hopefully gives you some overview of how you could do that. So I see there's one question, so I'll try to answer that. And then we're not using the add type annotation. No, there's no reason other than sometimes metals is so not working for me that I am hesitant to rely on it. But I mean, let's see if we can, if they very well. Okay, so that is why we are not using the add type annotation functionality, because having it tell us the types are any is not helpful. So that is the answer to that question. All right, I'm going to quickly check on the Discord to see if anyone has any questions. And otherwise, so okay, let me just go through a couple of these questions. So there was a little bit of discussion of like the last one wins, and when you get to like an atomic value, that's going to be the way it's going to be. You can imagine like the most primitive case is like if you have some flag that's true or false, and like one fiber sets it to false, and the other fiber sets it to true. Like there's like, what are you going to do about that? Someone's going to have to win. Or you could imagine maybe there's a FiberRef that has the executor you're supposed to run on. If one person says you're supposed to run on executor X and one person says you're supposed to run on executor Y, like you need to run on some executor, and there's no way to diff the executors because for your purposes, they are kind of atomic objects that you can't reach inside and modify or compose with each other. But the idea of this is for anything that does have some notion of different pieces of it, you want updates to be able to be applied to different pieces without clobbering each other. Then there's a question that actually got answered as well. Is FiberRef always created with unsafe? Is there a safe API? Yeah, so that's actually the one that we looked at the very beginning. So if I want to, I can always do, for FiberRef, in, all right, FiberRef.make 0 or wherever we want it to be. And that's a totally fine thing to do. And then you could use that in different parts of your program. But when you're using FiberRefs for this pattern, it can often be particularly nice to have them be static objects where you can just access them directly. And then this unsafe API can be very nice. So if you go back to ZIO, you'll see that pattern is used a lot. It's used for like logging context. It's used for what the loggers are. It's used for the chunk size in ZIO streams. It's used for the default level of parallelism for parallel operators for each par. So I think it's a nice pattern. You can definitely always create it this way, but then that just means you can kind of only use it in this block, or you need to explicitly pass it around. Versus if you use the unsafe operating, just create it an object, and you can just reference it anywhere. So I think it's nice that way. All right. Well, I think that was all the questions, and we are at almost an hour and a half here, which is usually my threshold for the longest patience people are going to have for a symposium. So I think we will break here, but I'll push this code up, and yeah, thank you so much, everyone, for joining. Really appreciate it, and really appreciate the questions. Oh, I see one more person's typing, so maybe I'll give you, if you get your question in the next minute, and I'll answer it. Okay, I think it's just a thank you. All right, awesome. Well, have a great weekend, everyone. Take care.